Okay, we're working through a method of joints problem, which is a little bit involved. So it takes some getting used to. This is problem 1 out of the book, chapter 4. So what we have is a truss, and it has joints A, B, C, and D. There's a 2,000 pound load here, 500 pound load here. We have a pin and a roller, so we're going to model these. So the first step in this process is to solve the reactions. And if you blow reactions on these problems, you're never going to get it to work. So the good news is that if you do blow them, you'll know it, but the bad news is that you'll go through a whole lot of work to get to that point. So what we're going to do first is go through this. We've got reactions, so we're going to solve those first. Sum of forces in X has to equal 0. So in X we have our AH, nothing resisting it, so that's 0. So that's nice. Sum of forces in Y have to equal 0. So in this case, we have quite a bit going on. So we've got our AV acting up as we modeled it, and our CV acting up as we modeled it. We've got 2,500 down. I'm just going to go ahead and bring this over on this side. So no solution yet. So we can take a moment. Clockwise moment positive. We're going to take it at A. We got, this is 10 feet. 10 feet. So we have 10 times 500, tending to turn that clockwise. That's a plus. Plus, again, another 10 times force 2,000. We have 20, tending to turn that negatively, so that gives us a negative RCV times 20 equals 0. So when we do that math, RCV turns out to be 25,000 negative divided by a 20 negative gives us a positive 1250. And the positive indicates that we were correct in our assumption initially. When we plug this in up here, we notice that our AB is also 1250 up. So if you blow the reactions, you're done with this process. So that's one of the important things. So what I normally do is I'm going to come back over here and I'm going to replace all of the unknowns now with the known information. And even though we have a 0 here, I don't discount it because I use it kind of as keeping track of what's going on. So I know that this is 0, this is 1250, and this is 1250. And I always use this little symbol to say reaction, 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 and these are external loads. So at this point, we're ready to start the process of the joints. And you have to start at a point that you have enough information. So for instance, A, we have 2 pieces coming in, 2 unknowns. We probably have enough here. We wouldn't have enough at B because we've got too many unknowns at D. C would probably give you also enough unknowns rather. So usually your best bet is to start at one of the reactions, either in this case, either A or C. So what I'm going to do is erase this information. We're going to start out with joint A, and we have to bring all that stuff back in. So you need to keep track of this. Obviously, you would be doing this on a piece of paper. So I'm going to let you guys. Okay, so we're going to start at A, and we're going to draw a free body diagram at A. So I'm just going to start out with what I know. So I know that I have a reaction, and it's 1250. And I have another reaction, which is 0, but I'm going to go ahead and indicate it. So I have two unknowns at this point, a member AD and a member AB. So I have to make a decision on which way those are acting. And you can, it's arbitrary, but if you look at the diagonal, a lot of times you can tell this guy will have a horizontal and a vertical component. And if this guy's going up, this guy's going to have to go down, which would indicate to me, as I look at this, that that is a compression member. So I'm going to call that AD. Now, if you do it wrong, you'll just get a negative sign for your answers, and you just roll with it. And as I look at this, I'm going to call this as a tension member. Okay, so we have a concurrent or a concurrent force system, correct? So all we have at our disposal at this point is sum of forces in X and sum of forces in Y. So what we're going to do is just do that, and if we can't resolve it with sum of forces in X and sum of forces in Y, we went to the wrong joint. So sum of forces in X. In X we have AD horizontal acting negatively plus AB is equal to 0. And so therefore AB is equal to AD horizontal. So we don't get any answers out of that. So we'll come over here, do our forces in Y. Sum of forces in Y have to equal 0. So in Y, what we have is 1250 up minus AdV. That has to be equal to 0. So this resolves. AdV is therefore equal to 1250. And since it's a positive, that does indicate to me that I did orient that in the correct direction. So now to get DH, we've got a geometric relationship between these two guys because there's a vertical distance of 15 and a horizontal distance of 10. So the vertical vector dV rather is to this distance as d horizontal is to this distance. So you can set up a proportion that says that ADH is to 10 feet as 1250 is to the distance over which it runs, which is 15. So ADH, when we do that math, resolves to 83.33. So that tells me now that AB is 83.33. And since it's positive, we called it tension, and that's what it is, it's tension. So if that was negative, it would be actually in a compression. So the other thing we need to do now is solve the actual value of AD, and what we have is two components, a horizontal and a vertical. So what we do is just use a Pythagorean theorem. And I'm going to just simply take, then say that AD is equal to 1250 squared, which is this guy, plus 833.33 squared, which is this guy. Taking the square root of that, that will give me AD. AD turns out to be 1502. You can round that. And that is a compression member. So when you get these answers, you have to put both the magnitude and the quality, tension or compression, okay? And so here's your two answers. There's the one answer. There's the other answer. So this joint resolves. So we're ready to go to the next joint, and we'll have to make a decision on what joint we're going to. But I would think if we look at this, B will probably be the joint that we're going to run to. So I'm going to go ahead and go to B. Okay, so then when we do joint B, we're going to have to bring all of the information in. So at B, here's my joint. I have an external load coming down at 500 pounds. Also, we solved this guy, AB. That turned out to be a tension member. So since tension is away from the joint, I draw it away. Notice in the other picture it was going the other way, so you've got to flip-flop them. And we need to bring in that value, and we solved AB as 833.3 approximately. Then we have this vector and that vector. So as we look at this, if we look at it, it's pretty logical. This vector right here, which is BD, has to be going up because it has to counteract that one, and this one has to be going right. So we're going to call this BD. We're going to call this BC. And by inspection, you can already figure these out probably, but if we just write the equations, sum of forces in X have to equal 0. In X, we have BC minus 833.3 has to equal 0. So therefore, BC is equal to 833.3. And we indicated it as tension. It's positive, so yes, it's definitely in tension as well. Sum of forces in the Y. In the Y, we have BD minus the external 500 has to equal 0. Therefore, BD is equal to 500, and it's also a tension member. So there's your one answer, and there's your other answer. So we have resolved a good chunk of this truss now. So now we could either go probably to D or to C. I'm going to go ahead and go to D, and I'm going to clean this picture up, and then we're going to go in and redraw the free body diagram. Okay, so for the free body at D, bring in everything that you know. First thing I always do is the external loads. I've got 2,000. We just resolved DB, and that vector was tension. So he's also acting down in tension. He's down at 500, I believe, is what we resolved that to be. And then we have this guy, and you have to be really careful with this. So when we solved that, that was vector AD, or member AD. We called that a compression member. So that means it's coming in to this one. And what you really want are the two components of this guy. And be careful so that you get the horizontal with the horizontal and the vertical with the vertical. So the horizontal in this case turned out to be 833.3, and the vertical component was 1250, I believe. Okay. Now be careful with these pictures because it's easy to flip-flop these. So now we just need one more here. That's the member DC. DC is the unknown, and it's going to have two components. If we look at this, it's kind of easy to figure which way this is going, because if you notice, that plus that is greater than that. So this guy would have to bring a vertical component. So I'm going to say this guy is actually acting as a compression member. I'm going to call this DC. So let's see what happens. So we take the sum of forces in X equal to 0. And for X, we're going to have 833.3 minus DC horizontal. So therefore, DC horizontal is equal to 833.3. So that is telling me it's a positive. That tells me that this is indicated correctly. And we're going to do one more. And then we're going to have a little check when we get done here. So we have 1250 up minus 2000 minus 500 plus DC vert has to equal 0. So at this point, when we do this math, DC vert, when you sum those guys up and bring them over to the other side, they resolve to 1250. Now, notice these are both positive, and they have to be both positive, because if one was positive and one was negative, that would send this vector another direction, and it has to be going this way. So the fact that they're both positive also indicates that we're probably in good shape. Now, we also can further check that we have a geometric relationship going on here. So we know that the horizontal is to 10 as the vertical is to 15. So we can write that out, that the horizontal 83.3 is to 10 as 1250 is to 15. So these should equal each other. And if you do the math here, this becomes 83.3. That's 83.3. This is a check. You don't have to do that, but at this point, it really tells me that I'm probably right where I need to be. So we need one more joint to do. We're going to do the joint at C. This is the final joint. And everything should resolve to 0 at this point. So once we do this, this is our answer. And if it doesn't go to 0, we got a problem. Okay, so at joint C, we're going to bring in everything for a free body diagram that we know, which is everything at this point. So we have a reaction here at 1250. We have a vector here, and that turned out to be all tension. So that's going to be 83.3. And we have this vector, which we consider that compression. And that's compression. And we have a vertical component and a horizontal component. The horizontal component of that vector was 83.3. The vertical was 1250. And you can see clearly that when I take the sum of forces in X and sum of forces in Y, in X we have 83.3 minus 83.3 equals 0. That checks. Sum of forces in Y is equal to 0. And that's 1250 up minus 1250 down. That's also equal to 0. That checks. Sometimes these won't go exactly to 0. You might have a little bit of rounding going on, so I wouldn't be too concerned. But if you get like 5 feet or 5 units here and 0, then you got a problem. And also, I got a little fast, so I forgot to actually calculate the magnitude of CD. So we could do that now. We know that that was 83.3 squared plus 1250 squared, square root. And that tells us that DC is 1502.3, and that was a compression member. So we have everything resolved at this point. Once you get to this, the last joint, and it goes to 0, you know you're good. So if this is out a lot, what that probably tells you is you've got a reaction issue. So the first thing I would do to debug this would be go back and look at your reactions. If this goes to 0, then you're good. But don't forget, when you do each member, you have to determine not only its magnitude, but also the quality, whether we're talking about compression or tension, because we have to know both things. Okay, so we're going to work a couple more problems, but that takes care of that one. This is problem 1 again.